right. Well, hello, good morning. I'm Paul Young. This is Chemistry 110, that's what it says. And I am your instructor for this semester. Let me tell you a little bit about me. I was a full professor at UIC for 37 years. Specialized in organic and biochem. Later on, I did general and intro, and here I am, finally after retiring. These are the textbooks that they say are recommended for the course. They say required, I think, but nonetheless, they are recommended. This is the book that we'll actually use, it's mine, and this is free. These are very pretty, but they're expensive. So it's up to you. I'm supposed to do this. Safety protocol, if you're sick, stay home, okay? Let me know. And you're supposed to write to Laura Hill and tell her you're sick so they can do contact tracing or whatever. Masks are not required. Only thing that is required is that you go to the bookstore and get goggles. It's a very nice look. Goggles with a mask was even neater, but this works. Any questions? All right. Email, I still use the UIC email. This is the one for Triton. If you want to talk to me about something, please send me an email and we'll set something up. Typically it's online through Blackboard, Collaborate, but whatever, we could set something up. This, what I just said, is the recommended text. They say 9th edition, maybe it's 10th by now, who knows. It's unchanged since about the 6th edition. The publisher simply makes you do a new edition every couple years so that your used book drops in value. It's not nice, but that's what they do. There's also a lab manual that's in the bookstore. I will give you handouts that have everything you need for lab. You may get the lab manual to read about the things, but you don't have to. Goggles, of course, are required. The book, Introductory Chemistry Online, is, if you want a hard copy, you could get it through Lulu. The one on Blackboard is an ebook, and it works perfectly fine. 2 websites. This is the Triton Blackboard. Please make sure you go there, make sure you can get in. We will use Blackboard extensively throughout the semester. This is my site, chemistryonline.com, and we'll talk more about that in just a couple minutes. On Blackboard, you will be able to download a handout for every lecture. I sent everybody a copy of the handout for today. The handouts are mini prints of selected slides. Sometimes they're a little out of date, to be honest, because I don't update these. I do, however, change my lecture up to like 15 minutes before I give it, so it's always out of date. The neat thing about these, though, in class we will do lots of problems. The problem is here, but there's no answer. So you get to learn to write very, very small and to play along. There's also lots of words here that you don't have to write, so you can listen to what I say. Any questions? You also have to have a calculator. The calculator on your phone might work for you, but it might not. The thing that's usually missing on the phone calculator is the ability to easily go to scientific or exponential notation. The functions that we will use most often are these guys, log x and 10 to the x. So make sure whatever calculator you have has this ability. If you want to just use your phone, there are apps that do it, but typically the default ones, getting into scientific notation is difficult. We will have 2 exams. I call them exam 1 and exam 2. We will also have 2 quizzes. The quizzes come just before the exams. I say they are cumulative, they are. Basically, it's everything you've learned since kindergarten, but mostly on the chapters we do immediately before the exam. The quizzes are given online through Blackboard. Again, there's lots on Blackboard. Make sure you can get in and you can do it. The point breakdown is pretty simple, 90, 80, 70, 60. We will have 2 exams, 2 quizzes. Lab work is worth 100 points. That's Wednesday in D204. And our final exam checks in at 200. Final exams are terrible things. This is the Chemistry Online website. The link here that you'd be most interested in is this guy down here, tutorials. We will do tutorials a lot during this semester. This is what the tutorial page looks like. Basically, it's a math review, and then we do chapter by chapter all the way down. These guys are algorithmic problem sets. So every time you do it, you will get a different question, different numbers, different answer, and if you get it wrong when you do it, there's a little button you can push and it will tell you what you did wrong. So it's kind of neat. I wrote these. I'm a wonderful teacher, but not a great programmer. So sometimes it works. Almost always it works, but sometimes it won't. Just give me space. Let's look at one. This is the math review. Now, in this class, in chemistry in general, we're going to deal with lots of big numbers, lots of small numbers. For that, you need to be able to do simple calculations such as this. This is under math review. You're supposed to know how to do this from 5th grade. In this one, we have 3.84 times 10 to the 8th divided by 2.39 times 10 to the 20. Now, there are 2 ways to do this. The old way, that's very difficult, and the new way. Let's do the old way first. We look at this and we say it's division. In 5th grade, they said when you have division, first thing you do is subtract the exponents. So 8 minus 20 is minus 12. Next, we would divide the 2 coefficients, get 1.61. On the tutorial here, you would enter minus 12 as your answer. It will tell you you're correct or not. The little button down here, show answer. This will appear, and basically it'll work you through the problem step by step. Now, that's the difficult way. That's the old-fashioned way. Why do I want you to do this? I want you to do this because I want you to practice using your calculator. This is my calculator. It's not as nice as yours, but it works. It has the exponential function, log, and 10 to the x. On my calculator, I would type in 3.84 times 10 to the 8th using the exponent button, divided by 10 to the 20th, and I get the answer. It's essential that you be able to use your calculator and to get this right, okay? So that's why I want you to do this, simply because you need to practice. You need to be able to whip through problems like this, no issue. Do we have any questions? Well, then, I guess we're going to start with Chapter 1. Chapter 1, we're going to talk about measurements and going to talk about basic atomic structure. Chapter 1 is relatively long, so we will do the first 3/4 of the chapter today. Next week, at this very same time, we will start Chapter 2, but we will finish Chapter 1 first. So, start off with the basics. That's matter. Matter is any substance that has mass. Remember, mass is different than weight. Weight is the effect of gravity on mass. Mass is an inherent property of an object. Matter, we will say, is composed of atoms, and atoms are composed principally of protons, which are positive, electrons, which are negative, and neutrons, which are neutral. Within the atom, protons and neutrons live in the nucleus, that's in the middle, and they're surrounded by electrons. Now, everyone knows what an atom looks like. Basically because in the 50s, the Atomic Energy Commission had this as their logo. So an entire generation grew up thinking that atoms looked like this. Had a nice nucleus in the middle, little electrons flying around it in orbits. The problem with this representation is that it's totally wrong. It's cute, but it's wrong. Electrons don't live in little orbits. They simply occupy space that's best described as a cloud. Somewhere within this cloud, surrounding a nucleus, there are electrons. We don't know where, but they're there. Typically, you do a 90% probability. This is about the region where you will find the electrons. The other thing that's wrong here is the nucleus. The nucleus is not a big ball sitting in the middle. In fact, the nucleus is so tiny. This represents an atom of helium. This is the electron cloud. And the nucleus, with 2 protons, 2 neutrons, is here. Now you can't see it because it's tiny. When I did the graphic here, I put a single pixel to represent it, but you can't see that. Atoms are very, very small. If you have a copper penny, it would have roughly 28 sextillion copper atoms. Now you won't have that in this penny. This penny is zinc with a thin coating of copper on it, but that's copper. So this guy would have 28 sextillion copper atoms. If there's so many in a single penny, they're obviously very small. Hello? Okay, well, PowerPoint does that sometimes. Obviously, atoms and subatomic particles are very small. The mass of a single proton in the nucleus of a copper atom is roughly 1.67 times 10 to the minus 24 grams. Now this is scientific notation. This is what the number looks like in decimal format. We will talk about scientific notation and converting one to the other in just a little bit. Basically what we're saying here though is that we must move this decimal point 24 places to the right in order to get our coefficient. A neutron has a mass very similar to that of a proton, and electrons are much, much smaller. They have virtually no mass, and this brings up the realization that in an atom, virtually all of the mass is concentrated in this little teeny tiny nucleus. Atoms are basically all empty space. Amazing. To put this more in perspective, this is the old Wrigley Field, okay? If you look at this picture very, very closely, right there in the infield, there's a golf ball. There it is. So, if the nucleus was the size of a golf ball, the electron cloud would be the size of the entirety of Wrigley Field. Once again, extremely tiny, huge, huge electron cloud with almost no mass. Now, talk a little bit more about atoms. If you have a substance that has only one type of atom, that's called an element. There are 118 or so known now. Every element is identified by a chemical symbol. Quite often, those are based on the English name. That makes it simple. Helium is He, for example. But some of the elements that were discovered a long, long time ago still have Latin or Greek names. For example, ferrum is iron. We display the elements on what's called the periodic table. Looks something like this. Here's one that we will use. And here are some representative elements. H is for hydrogen, that's simple, Be beryllium. Mg for magnesium. Ca for calcium. Carbon is a C, helium is He. But there's lots of ringers in here too. Silver, for example, is Ag. Gold is Au. Lead, Pb. Tin, Sn. Antimony, Sb. Copper is Cu, not Co. That's cobalt. These are very common. Sodium is Na. Potassium is K. Again, these are Latin names. There's a starter list that's available in your handout, I believe. These are ones that we talk about a lot. Kind of make sure that you are familiar enough so that if I say boron, you know it's a B. Now, like I said, there are 118 elements. Some people are compulsive and they want to know all of them. That's okay, you can do that. There are almost sentences that have all of the element in there somewhere. I don't know how in the world you're supposed to remember the sentence, but you can. Or my favorite method to remember them all is the song.
There's antimony, arsenic, aluminum, selenium, and hydrogen and oxygen and nitrogen and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, ytterbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bismuth, bromine, lithium, beryllium, and barium. There's holmium, and helium, and hafnium, and erbium, and phosphorus, and francium, and fluorine, and terbium, and manganese, and mercurium, molybdenum, and magnesium, dysprosium, and scandium, and cerium, and cesium, and lead, praseodymium, and platinum, plutonium, palladium, promethium, potassium, polonium, and tantalum, technetium, titanium, tellurium, and cadmium, and calcium, and chromium, and curium. There's sulfur, californium, and fermium, berkelium, and also mendelevium, einsteinium, nobelium, and argon, krypton, neon, radon, xenon, zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. These are the only ones of which the news has come to Harvard. And there may be many others, but they haven't been discovered.
Well, that's fun. Actually, I once, when I was younger, sang that for the class of 500 people at UIC at 8 o'clock in the morning. It was fun. I don't do that anymore, though. Like I said, we arrange all of these elements in a periodic table. Now, the very first periodic table was published by Russian chemist Mendeleev back in 1872, and it was a really great advance. He put things by what today we call periods and groups. Now he misspelled table and misspelled group, but aside from that, he organized the elements by the way they react with oxygen and hydrogen, and pretty much got it right. That's amazing for the day. Today, we label our groups across this way, periods go up and down this way. Now, there are 8 major groups that we will talk about. I know that there are 18 little slots across here, but we're going to stick to the 8, and by the time we get to chapter 3, I believe you'll understand why. It just makes it easier to do some simple things. We could also use the periodic table as a bit of a grid. So if I asked you something like, what atom is in group 1, period 4? You can do that. Group 1, go down to period 4, we get K. Remember, K is one of our exceptions. That's potassium. Group 2, period 6. The 6th period, the 2nd group, Ba. That's barium. And over here, group 8, period 4. 8, 4, Kr. That's krypton, not kryptonite, krypton. Any questions? During lectures, you're sitting here, you're thinking lots of things to yourself, I'm sure. And one of the things that always comes to mind is this going to be on the test, right? So, during a lecture, I tend to always put in exam questions. So these are typical exam questions from the past. In this one, I asked you to identify the symbols for copper, carbon, and cadmium. Now, copper. Remember we said copper was not Co, that's cobalt, it's Cu. So we're down to these 3. Carbon we said was a C, so it's these 2. Cadmium we haven't talked about yet, but we did say that Ca was calcium. Therefore, this is the best answer. Another simple question. Which has two letters? Well, fluorine is an F, phosphorus is a P, oxygen is an O, nitrogen is an N, and remember silver? It was Ag, gold, Au. Na, remember natrium, not neon, potassium, nickel, it is sodium. This is a very simple one. Which one only has one letter? Iron, we said, was Fe, antimony, Sb, Sn, Na, phosphorus, again, is a P. Everyone always confuses phosphorus and potassium. The symbol for potassium, remember, is a K. Kelly. Any questions? All right, well, let's continue with our discussion of atoms. If you look at the periodic table, every element up here is arranged in numeric order, from 1 down to 118, okay? This is called the atomic number. The atomic number simply is the number of protons in the nucleus. That is the thing that defines what the element is. If it has 6 protons, it's a carbon. Doesn't matter how many electrons it has. Doesn't matter how many neutrons it has. If it has 6 protons, it's a carbon. That is its atomic number. We can represent this using something called the atomic symbol. The atomic symbol consists of the symbol for the element, then as a subscript, the atomic number, that number of protons, and as a superscript in front, mass number. Now remember we said that the mass of an atom is basically protons plus neutrons. That is what is called the mass number and is simply the sum. Writing this on a word processor is virtually impossible, but nonetheless, that's the way it is. Let's go ahead and do some. Hydrogen, helium, lithium, and beryllium. For hydrogen, the symbol is H, so we would begin by writing H. The atomic number is 1 proton. So we put that as a subscript in front. The mass number goes up here, and it's the sum of protons and neutrons. Hydrogen typically doesn't have neutrons, therefore the mass is 1, and that is the symbol. Lithium, the symbol is Li. Atomic number is 3, so that's 3 protons down here. 3 plus 4 is 7, that's the mass number, it goes here. Do helium, He. Atomic number of 2. Mass number of 2 plus 2, 4. And finally, beryllium, symbol is Be. We have an atomic number of 4, goes here. We have a mass number of 4 plus 5, and it goes there. Any questions? All right, I did the simple ones. Go ahead and quickly do these guys. The symbols are O, C, Potassium, not P, it's a K. And iodine is an I. Our symbol is O. Our subscript in front is an 8. The superscript in front is a 16. Potassium. Our symbol is a K. Atomic number is 19. That's our subscript. 19 plus 20 is 39. Carbon. Symbol is C. Subscript is 6. Superscript is 12. And finally, iodine. The symbol is I. The subscript is 53. And the superscript, I can do this without a calculator. Yes, I can. 127. Yes, I got it. Any questions? On an exam in the past, I have done something boring and said, write the atomic symbol for something. Okay? But a much more interesting question is something like this. Here we have a neutral element with 12 electrons and a mass number of 24. Give me the period, the group, how many neutrons, and the atomic symbol. Think about it for a moment. Well, what you're saying to yourself is, okay, I could do this if I knew what the element was, right? Gee. The trick here, this is a neutral element with 12 electrons. Electrons are negative. In order for this element to be neutral, it must have 12 positives, right? That's 12 protons. Therefore, neutral element, same number of protons as electrons. 12 electrons, 12 protons. Atomic number, 12. We're doing magnesium. Okay, magnesium is in the third period. It's in group 2. Now, if the mass number is 24, and 12 of them are protons, the other 12 are neutrons. So we would write the atomic symbol as magnesium, subscript 12, superscript 24. Any questions? Well, that was fun. And I'm sure you would really like to do more examples of that, right? Fortunately, you can. If you go to Chemistry Online, atomic configuration of elements and ions, I lovingly call this one protons, electrons, and neutrons. What it is a table with holes in it. And what you do is you simply type in the appropriate numbers. So, our symbol is SN. protons, we need to look at a periodic table, don't we? So before you do this, go to Blackboard. The periodic table we use on exams is there. Click on it. It looks basically like this one. And print yourself a copy. Here's one. All right. Sn is 10. We've said that. Where does 10 live? It's down here. Atomic number is 50. That means it has 50 protons. Now, if it has 66 neutrons and 50 protons, you simply add those up to get the mass number. Now, this 10 has a charge of +1. If the charge is +1, that means it has one more proton than it does electrons. Remember, these are positive, these are negatives. Has to be an imbalance. If there are 50 protons, 49 electrons. Look at this one. We're dealing with bromine. Look at our table. Bromine is here in group 7. Right here, atomic number 35. Go ahead and fill this in. Atomic number is 35, that's 35 protons. If we have 44 neutrons and 35 protons, the mass number is 79. Now here our charge is -1. That means we have one more electron than we do proton. So if we have 35, this must be 36.
Sorry, where did the neutrons get the neutrons from? Yes.
Neutrons? Well, those were given here.
Oh.
So, and it changes every time you get a problem, what's given, what's not. Everybody's favorite heavy element is uranium-235. We look at our periodic table, and it's not here. Well, that's because it's down here in the bottom. Here it is. We'll talk about why we have this group of elements at the bottom. They're called lanthanides and actinides, but we'll talk about that in just a minute. But uranium is here. Atomic number 92. So that's 92 protons. Mass number is 235. 92 of those are protons. Subtract 92 from 235. We get 143. And finally, the charge. We have 92 protons, 92 electrons. This guy is 0. Any questions? Well, let's just pretend that you're there doing this and having a good time. I hope you are. And you get a bunch right. When you get the 5th one right, this shows up at the bottom. In the old days, here at Triton and at USC, if you completed 5 problems correctly, you could enter your email, click the submit button, and I would get notice that you had done this and gotten 5 correct. That was good, right? That's the way we used to do it here at Triton. But believe it or not, in every class there were 2, maybe 3 people that could never figure this out. Never figured it out. They sent emails everywhere. Not to me. So, I've decided we're not doing that anymore because it's just too much work trying to trace down these emails. Instead, after you've done this and you're good at it and you're ready for it, go to Blackboard. On Blackboard, you're looking for a folder called Tutorial 1 under Course Materials. Click on Tutorial 1 and you'll get a problem like this. It's a Blackboard quiz is what it is. Now you get to do this quiz as many times as you want. In this case, you would simply fill in the appropriate missing blanks. Sometimes you get everything except the symbol, have to plug that in, whatever. It's all under Course Materials, Tutorial 1. Now, like I said, this is a quiz. Blackboard's going to grade it. There are 5 questions, so you can get up to 5 points. Those 5 points are then added to your exam 1's score. Oh my goodness. Yeah. And there are 14 tutorials we will do before the first exam. Oh my goodness again. Do these tutorials. They are extremely important to your grade. They're great practice for exams. Quite often I will just go to the tutorials, pull a question off verbatim, stick it on the exam. Oh my goodness. Only problem is if you go to Blackboard right now, actually you can't see tutorials 2 either, but there is no tutorial 1. That's because we have lab safety this week on Wednesday. In order to see tutorial 1, you have to click on this link first. And you will then complete the lab safety contract. Looks like this. All you do is you click here, read all the nonsense, click here, and ask some questions. Are you colorblind? Are you pregnant? Are you whatever? Okay? Then you verify that yes, you have, and you read all these terms, and you're good. At that point, once you're done with this and you submit it, by George, tutorial 1 shows up. Any questions? Do the tutorials. All right. Let's talk about the concept of isotopes. We said that the thing that defines what an element is the number of protons. Carbon typically has 6 protons, 6 neutrons. If we were to write the atomic symbol, it would look like this. Okay. I also said it didn't matter how many electrons you had, how many neutrons you have. Carbon has 6 electrons. They're actually arranged in 2 energy levels. We'll see at the end of the chapter that this corresponds to the period that it's in the periodic table. But that's later. All right. If I take this carbon nucleus and I were to add another neutron to it, I would get a heavier version of carbon. It's still carbon, because it still has 6 neutrons. With carbon, you can do this twice. And we get a carbon with a mass number of 14. These are called isotopes. They're the same element, they just have different mass numbers. Now, typically we would write them this way: carbon 12, 13, and 14. This represents a slight problem when it comes to weighing out a certain number of carbon atoms, because it's a mixture of different mass numbers. How do you do that? Well, what we're going to do is determine an average mass. Now, it turns out that chemists have been very clever. They figured out a way to determine for carbon on Earth, 98.89% is carbon 12. A little over 1% is 13, and just a tiny trace is 14. We can take the fraction, this 12, multiplied by the mass, add it to the fraction that's 13, we can ignore 14, and we get an average atomic mass. When you look at the periodic table, see these little numbers underneath, those are all average atomic masses. If you look at carbon, 12.01. It's the average atomic mass. Whenever you do calculations, you will use the average atomic mass. Now, interestingly, within our solar system, it's almost constant from planet to planet, although unlike oxygen on Mars has a different average atomic mass than it does on Earth. So, and in galaxies far, far away, totally different. It all depends on how the elements are formed. Okay, so that's average atomic mass. Let's look a little more at our periodic table. The ones that I typically use in the slides here are colored. They're colored for a reason. The blue guys here are what we refer to as metals. They all have similar properties in the fact that they conduct electricity, they're malleable, whatever. Certain type of bonding, metal bonding, whatever. The yellows over here are what we call nonmetals. These conduct electricity, these don't. These are malleable, these are brittle. In between, we have this little strip of green. It's the transition between metal and nonmetal. These are called semimetals or metalloids. And these guys, these are the semiconductors that we use to make transistors, computer chips, and stuff like that. These, the 1 through 8, are referred, kind of old nomenclature, but they're called representative elements. There was a time when they thought that these guys were what you found in living things. They were wrong. Actually, whole bunches of these guys also show up in living things and are very important in enzyme function. These guys are the transition. They're a transition from this group of representative elements to this group. They're all metals, and they're called transition metals. These guys down here are the inner transition metals. Now, why are they stuck down here? Actually, in the table, these go here after lanthanum and actinium. So the periodic table really looks like this. And here's our inner transition elements. Now the problem is that this is a stupid looking table, number one. You could never fit it on a sheet of paper. If you did, you could never read it. Therefore, nobody really cares about these guys anyway, so we just pull them out and stick them at the bottom. Over here we have in group 8, these are collectively called the inert gases. They're also called noble gases. Inert gases do not react. They don't do anything. Neither did nobility. Next to it, we have a very important group called the halogens. The important ones are fluorine, chlorine, bromine, and iodine. We'll see those a lot. Basically very reactive. Speaking of reactive, group 1 collectively are the alkali metals. These are so reactive, with the exception of hydrogen, that's a non-metal. But these guys are so reactive that they will react instantly with water. Group 2, alkaline earths, also react with water, but much more slowly. Now, there are lots of ways that you can do a periodic table. This is a classic. This is one of my favorites, though. You can take it and wrap it into a little circle. The nice thing about this is that you can let it small, stick it in your pocket, whatever. Now, I find that interesting and pleasing because when I was a student, many, many, many years ago, there was no such thing as a calculator, believe it or not. Instead, we used slide rules. Slide rules were amazing critters. Slide this thing back and forth, slide this back and forth. They were huge, 14 to 18 inches. And, you know, the bigger it was, the better you were, I guess. And you could do amazing math on them. You know, this is how we got to the moon, really, with a slide rule. Incredible. Well, I was in the bookstore one day, again, many years ago, with my slide rule, 18 inches, and I saw this. It's so cute. And it fit in your shirt pocket. And it reminds me, well, that periodic table reminds me of my favorite little slide rule. And you didn't need the big sucker anymore. So that's why I like this table. Nonetheless, I diverge. Any questions? Let's do some more problems. Phosphorus 32 is a radioactive element, and it is used in chemotherapy, actually. How many neutrons are in this isotope? Well, remember, we have a mass number, don't we? We look at our periodic tables. We have the number of protons. The mass number is sum of protons and neutrons. 32 minus 15, 17. Bromine 79. How many protons, neutrons, and electrons? Well, atomic number is 35, so it's 35 protons. All of these are 44 neutrons. That gives you 79, so it could be one, could be all of them. How many electrons? Well, again, the key word here is neutral. If it has 35 positives, it must have 35 negatives. Any questions? All right, like I said earlier, in chemistry and in science in general, you're going to deal with very large numbers and very small numbers. 28 sextillion, you would never write it out this way. Instead, you would write this, 2.8 times 10 to the 22nd. You would never write the mass of a proton with all these zeros in front. Instead, you would write 1.67 times 10 to the minus 24. This is scientific or exponential notation. What we're going to talk about is how to take decimals like this and simply convert them into scientific notation. It's actually very simple. What you're going to do is take your number. You're going to look at it. If it has a real decimal point, you're going to see how many places you have to move that decimal point so that it's between the first or after the first non-zero digit. Next, you're going to look and see how many decimal places you had to move it. If you move it to the left, your exponent will be positive. If you move it to the right, it will be negative. That's it. So, 950,000. You look at it. Well, it doesn't have a decimal point, does it? But it has an implied decimal point. We know that there should be a decimal point here. Okay? What we're going to do is move this implied decimal point so it's between the 9 and the 5. Our coefficient then is 9.5. Next we look and we see, how did we do that? Well, we started here. We moved to the left 5 places to get 9.5. To the left, it's a positive. We have 9.5 times 10 to the 5th. That's it. Let's do another one. Let's do a bunch. Rewrite all of these using simple scientific notation. On our first one here, we're going to move our decimal where it is, in between the 2 and the 5. We get 2.57. Now, right now, we're going to put all of the real digits down. We'll see why in just a few minutes when we talk about some significant figures. But all right. So we move this to the right 2 places. To the right is a negative, so this is minus 2. Our next one, we're going to start here. Going to move it to the left 2 places, so it's in between the 1 and the 2. Moving to the left 2 places means it's a positive exponent, and it's a plus 2. $93 million. No real decimal point, but the implied decimal point is here. We're going to move it between the 9 and the 3. To do that, we had to move to the left 1, 2, 3, 4, 5, 6, 7 places. So it's a +7. Doesn't matter if it's plus or minus. Here we're going to take the implied decimal point, move it between the 6 and the 5. We had to go to the left 1, 2, 3, 4 places, 10 to the 4th. Finally, this guy. We're going to take the real decimal point here and move it between the 2 and the 7. To do that, we had to move 1, 2, 3, 4, 5, 6 places, 10 to the -6. Any questions? Well, if you can do it forward, by George, you can do it backwards too, can't you? Rewrite these guys in decimal format. Now, when you're going from scientific notation to decimal format, the rules change as to right or left. If it goes to the, well, if it's positive, we're going to move it to the right. But same rule. We're going to move this decimal point 2 places. So 1, 2 to the right, 257. Now this next one, it's a negative exponent. So we're going to move our decimal this way. It's -7, so we're going to put 6 zeros in front of the 1. The number you would get is something like this. Now this is correct, but it's not convention, okay? It looks a little better if you put a 0 in front of this as well. Don't have to, but it just looks nicer. 0.125. I'm going to move this way 4 spaces, 3 zeros in front, plus an extra 0. 10 to the 4th. We're going to start here, move it this way 4 places. 1, 2, 3, 4. Decimal point right here. Now we'll see why this has all of these digits in here, again, when we do significant figures. Our last one, 10 to the -1, just going to move it over 1 spot, and we're going to put in a 0 in front. Any questions? Well, if you're wondering if there's a tutorial for this, of course there is. It is here in scientific and decimal notation. And it looks something like this. Click New Problem to get a problem, check answer, show answer, whatever. Again, show answer, it shows up down here. Here's our number in decimal format. We're going to put our coefficient here and put our exponent here. The coefficient is going to be 8.3. To get our 8.3, we had to move it to the left 1, 2, 3, 4, 5, 6, 7 places, 10 to the 7th. Here's our decimal point. We're going to move it to the right 2 places, so it's a negative. Our coefficient is 4.6. Right two places, -2. Going backwards, 7.1 times 10 to the -7. We're going to have 6 zeros in front of this, decimal point, and then another 0 just to make it look nice. .6 times 10 to the 7. Again, we're going to write our 5.6 out here. Move this way, we're going to put 6 zeros after the 6, and it's 56 million. One more. We're moving to the right. 1, 2, 3, 4, 5, 6 places. Our coefficient is 6.1. 1, 2, 3, 4, 5, 6. So it's -6. Now, the Blackboard version of this, you have to enter it in what's called E notation. Okay? E notation. A long time ago, Blackboard required a lowercase e for the E notation. If we had 0024, you would write it 2.4 e -3. That's our coefficient here. Without telling anyone, one day, they changed to only accepting an uppercase E, which I suppose didn't affect many people, but I had hundreds of problems online that I had to redo. Okay, that was bad. But I got them all done. So, 1700, 1.7 E3. They just came out with a new version of Blackboard. And yes, they did change it. But now they accept both upper and lowercase. So that's okay. Anyway, this is how you do E notation. When you do this on Blackboard, you must do it. Okay? All right. Let's talk a little bit about the metric system, because that's what we're going to use for measurements. Measure of length, the standard is a meter, roughly a yard. Standard of mass is a kilogram. Actually, we weigh most things in the lab in grams. Standard of volume is a cubic meter. Nobody ever uses cubic meters. This is cubic centimeter. Cubic centimeter is a cube. It's 1 centimeter on a side. This is what we typically use for a volume measurement. If you're measuring the volume of a liquid, however, instead of using cubic centimeters, you use liters and milliliters. A milliliter is exactly equal to a cubic centimeter. 1,000 mils is 1 liter. For liquids, this is typically what you will use. But remember, this is identical. Now, I'm sure you're thinking to yourself, what is it with the little k and the m and stuff like that? Those are called metric prefixes. It's a shorthand way of writing an exponent. If you write a lowercase p in front of your unit, measurement or whatever, a meter for example, that would be a picometer. P simply stands for 10 to the minus 12. Nano, 10 to the minus 9. This is the Greek symbol mu. It's micro, 10 to the minus 6. Milli, 10 to the minus 3. Centi, 10 to the minus 2. Giga, 10 to the 9th, 10 to the 6th. Kilo is 10 to the 3rd. If we just look at milli here, Whenever you put the little m in front of a unit, you're multiplying that by 10 to the minus 3. So 10 to the minus 3 meters is simply abbreviated as millimeter. The little m stands for 10 to the minus 3. Now, we are going to use, in a second, a problem-solving algorithm that we will use all semester. And it employs ratios. One of the things you use these ratios for is metric conversions. So if I give you something in micrometers and I ask you how many picometers that is, you will use this measurement algorithm. We do it by taking this simple thing here. 1 millimeter is the same as 10 to the minus 3 meters, right? We could write this as a ratio this way. 1 millimeter is the same as 10 to the minus 3 meters. This ratio is 1. They're identical numbers. So you could write this way or flip it upside down. Again, we will use these for metric conversions. For example, if we wanted to convert millimeters and meters, you could do this using this ratio. 1 millimeter, 10 to the minus 3 meters. That's 1. We could also say, if we had 1,000 millimeters, that would be 1 meter. Okay. This works because this is 10 to the third. Remember, this one is 10 to the minus 3. So 10 to the third times 10 to the minus 3 is 1. And because these ratios are 1, we can flip them all upside down. So for any conversion, you can write 4 ratios. Let's practice writing some ratios. Let's do meter and picometer. First thing you have to do is remember what pico is. We'll cheat and look at our table. Pico is 10 to the minus 12. So 1 picometer is the same as 10 to the minus 12 meters. We could also say, if we had 10 to the 12 picometers, that would be 1 meter. And of course, you can flip them upside down. Let's do it again. Meters and micrometers. Micro, 10 to the minus 6. The simple one is 1 meter or 1 micrometer, 10 to the minus 6 meters. We could also say if we had 10 to the 6 micrometers, it would be 1 meter. Last one. Nanometers. Nano is 9. 1 nanometer is 10 to the minus 9 meters. If we have 10 to the 9th nanometers, we have 1 meter. Very simple. Now, like I said, this ratio algorithm that we're going to use it throughout the course. In fact, this is so simple you could use it for virtually every science course you ever take. And it's very simple. It's the given find ratio. You're given a number in a problem. You're going to set up a ratio from the units you are given to what you're trying to find. Simply multiply these out and you get the answer. The only rule is that in this ratio, whatever units are given have to be in the denominator. So if we were given meters and we wanted to find kilometers, you could say 1 kilometer, kilo is 10 to the third. 1 kilometer is 10 to the third meters. Again, meter in the denominator. Let's look at a real problem. Here we just happen to have 6,000 kilometers. The question is, how many meters is that? Our given is our 6,000 kilometers. We need a ratio between kilometers and meters. There are two. 1 kilometer, the K is 10 to the third, so 10 to the third meters, or 1,000 meters in a kilometer. The rule is the ratio must have the units of given in the denominator. So we want this guy. We start off with our given. Plug in our ratio. The reason it has to be in the denominator is so they cancel. 6,000 times 1,000, we are looking at 6 times 10 to the 6th meters. We will use this method a lot. Again, the more you do it, the better you are at identifying the ratio you need. Let's just practice on a couple. If we have grams and we want kilograms, first thing you say is, we need a ratio with grams in the denominator. Kilo is 1,000. We could say 1 kilogram is 1,000 grams. So you would then multiply given by this ratio, grams will cancel, and you get 2 kilograms. Meters and micrometers. Micro is 10 to the minus 6. Meter must be in our denominator. So one of the ratios we could write is this. 10 to the minus 6 meters is 1 micrometer. Multiply 10 to the minus 7 by this, and you get 0.125 micrometers. Grams and nanograms. Nano is 10 to the minus 9. Gram has to be in our denominator. We could write 1 nanogram, 10 to the minus 9 grams. Multiply 9 times 10 to the minus 4 by 1 over 10 to the minus 9. You get 10 to the 5th nanograms. Meters, kilometers, gee, we've done that. Kilo is 1,000. Meter in our denominator. 1 kilometer, 1,000 meters. Multiply this by this, 65.8 kilometers. And finally, one that is going to be very common, grams and milligrams. Milli, remember, is 10 to the minus 3. we could write this with gram in our denominator, 10 to the minus 3 grams, 1 milligram, multiply it out, 278 milligrams. Now, there did not used to be a tutorial for this, but a couple years ago, class whined so much that I wrote one. That's difficult now. It's always been difficult. But it looks something like this. Simple metric conversions. 3 grams into kilograms. Our given is going to be our gram. We're going to need a ratio with gram in our denominator. So we could do something like this. 10 to the minus 3 kilograms is 1 gram. Remember, kilo is the same as 10 to the third. So this is 10 to the third times 10 to the minus 3, which is 1. So that works. There's another ratio you could write too, but this one works. Simply multiply 3.04 times our ratio. Grams will cancel. 0.0304. This is, if you click on Show Answer, this is what you get. Again, the neat thing about this that makes it a tutorial is that this is specific for whatever question I ask. And it changes every time, so you can just do it as often as you want. Do another one. Milliliters to liters. Remember, milliliter is the same as a cubic centimeter. There are 1,000 of these in a liter. So, milli to liter is our given. 10 to the minus 3 liters is 1 milliliter. You're going to take this, multiply it out. 2510, 10 to the minus 3, 2.51 liters. Any questions? Remember, when you do this tutorial in Blackboard, you just do e-notation. Again, 1700, 1.7, E3, no spaces. Any questions? The one measurement that we haven't talked about yet is temperature. We all know that freezing is 32 degrees Fahrenheit, boiling is 212. Forget that. That's Fahrenheit. In chemistry and science in general, you will use a centigrade or Celsius scale. Water freezes at 0, boils at 100. I will never ask you to convert Fahrenheit to centigrade or the other way around. However, there is another scale that you need to know, and this is Kelvin. Now, these might look like funny numbers. When we do Chapter 9, we will understand where these numbers come from. But the convenient thing is 273, 373, there are 100 little degrees in between, just like the centigrade scale. So we have centigrade and Kelvin as our two measurement units. Now, speaking of measurements, whenever you do a measurement in science, you want to do it as accurately as you can, right? We were measuring a temperature, for example. In order to express how accurately you did a measurement, you use what are called significant figures. Significant figures basically describe the accuracy of your measurement. For example, here's a ruler, and here's an arrow. And if I say, where's the arrow pointing? Well, you look at it and say, well, there's 50, 51, 52, 53, 54, and it's somewhere in between 54 and 55, right? We know it's at least 54. We know it's not 55. So we're going to look at this and say, well, 54 and a half. Sound good to me. If I were to say it was 54, that would be wrong. If I said it was 54.66666, that would be stupid. We don't know that. All we know is that it's somewhere in between 54 and 55, and it looks like it's in the middle. This measurement has 3 significant figures. 2 of them we're sure of, and the last one is our best guess. All measurements in science should have all the digits you're sure of, and then your best guess for the last one. The digits you're left with are the number of significant figures. Now, that typically doesn't give people problems as far as looking at a number and me saying how many significant figures. Because you just look and say, okay, you're sure of this, and that's a guess. Where people do have problems, however, are numbers that have zeros in them. So, a couple simple rules. First, you look at your number, see if it has a decimal point. Well, it does. In this number, then, there are leading zeros. That's zeros in front of the real digits. They're never significant. They don't count. They're not part of the measurement. This is a trailing zero. It's always significant. It's part of your measurement. When you measured this, you said, yeah, well, it's pretty close to 0. If your number does not have a decimal point, trailing zeros are never significant. They're not part of the measurement, only the ones in front. And if you have a 0 in between non-zero digits, they're always significant. So let's look at some. Here's our 3400. First thing we say is no decimal point. The rule says if it doesn't have a decimal point, trailing zeros are not significant, and we're left here with 2 significant figures. Here we have our decimal point. Our leading zeros are never significant, so they're gone. It's the trailing zero, it's part of the measurement, 2 significant figures. Another decimal point. Leading zeros are gone. This is a 0 in between other digits. It's real. We have 3 significant figures. No decimal point. The last 0 goes. This is real. 3 significant figures. How about 6.02 times 10 to the 23rd? Big number. If we converted this to decimal format, what would it look like? Well, we would move our decimal point 21 spaces this way and we get that number. But these are all trailing zeros, aren't they? They're not significant. We have 3 significant figures. When you write a number in scientific notation, the coefficient should contain all of the significant figures. All of them. Any questions? Well, let's do 2 problems in one here. Take these numbers, mentally determine how many significant figures they have, and then write them in scientific notation. Our first number, we look at this. Leading zeros go, we have 3 significant figures. We are going to write this 2.57. Move our decimal point 2 places. That's a -2. Our next number, we have a decimal point, but we have no zeros to worry about. So there are 4 significant figures. To make this scientific notation, we're going to move to the left 2 spaces, write all of our digits, 1.256 times 10 squared.
How many significant figures is there?
There are 4. All of these are real. That was your measurement. You're sure it's 125, and it's a little bit over halfway. 93 million. No decimal point. These all go. 2 significant figures. We go 1, 2, 3, 4, 5, 6, 7. That's a +7 exponent. Now think about this next one. We have a decimal point. What does that tell us? It tells us that all of these zeros are part of the measurement. It's a real number. When we measured it, it was essentially 0. Okay. So there are 1, 2, 3, 4, 5, 6 significant figures. All 6 have to show up in the coefficient. All of them. To get our coefficient, we're going to move this 1, 2, 3, 4 places. That's a +4. And that's our number. And finally, leading zeros go. We are left with 3 significant figures. Going to move our decimal point 1, 2, 3, 4, 5, 6 places. That's 10 to the -6. Well, on an exam, I could do a really boring question, couldn't I? How many significant figures in a certain number? I've done that. But one year at UIC, I decided I was going to be inventive. And so I came up with this question. Arrange these in order of decreasing numbers of significant figures. Now, writing the question was easy, okay? It didn't dawn on me as I did it, however, that there were 500 students in this class, and somebody had to grade this question, and that was very, very difficult. I've never done it again, but it's nice in lecture. Look at our first one. Leading zeros are gone. We have two significant figures. All of these are between real digits. We have 1, 2, 3, 4, 5. Decimal points, so they're real. 1, 2, 3, 4, 5, 6, 7. No decimal point. These go. We have 4. Decimal point. We have 1, 2, 3, 4, 5, 6, 7, 8. No decimal point. We have 3. So the winner here, 8 significant figures. We had a 7, right? Yep. Then we have a 5, I think. There's a 4, a 3, and finally a 2. See, I can do it. Now, everybody's favorite tutorial, both on Blackboard and on Chemistry Online, is this one, significant figures. How simple can it be? You're given a number. How many sig-figs do we have? Well, no decimal points, so we have 1, 2, 3. Decimal point, everything is real. 1, 2, 3, 4, 5, 6, 7, 8. Scientific notation, that's even easier. Everything here is real. That's a 4. Decimal point, the leading goes, this one stays, it's a 2. Like I say, it's everybody's favorite. Nice, simple way to earn 5 points. Now, the tutorial on Blackboard is slightly more complicated than the one online because, trying to spice it up a little bit, I put in calculations. There are 2 rules for dealing with significant figures in calculations. It's just 2. If you're doing addition and subtraction, you really don't look at the number of significant figures you have. Only thing you look at is your number and the number of digits after the decimal point. That's the only thing you look at. So, if this was your problem, feed these into your calculator, you would get 4.655. Now, if you look at the number of places after the decimal point, we have 3, we have 1. That means this guy must be rounded to 1 number after the decimal point. Look at the number of digits after the decimal, round to that number. For multiplication and division, it's a little easier, it makes more sense. You look at the numbers you have. Whichever number has the fewest significant figures, that's the most you can have in your answer. Okay? So here's a problem then. Here we have 3 significant figures, here we have 2. Calculator answer is this, 0.294. We must round this now to 2 significant figures. The least accurate measurement always wins. Aside from that, the tutorial on Blackboard is pretty much identical. All right, do we have any questions? Remember, today we covered exponents, significant figures, scientific and decimal conversions, metric conversions. On next Monday, we will do this one, atomic configuration. Each of these is worth 5 points. You must do the lab safety link first in order to see the tutorials, but get started. That's 20 points from today, extra credit for your first exam. Oh my goodness. All right, that's it. Have a good day. I will see you Wednesday. You don't need safety goggles on Wednesday, but after that we do. Oh, and I forgot to say, assuming that everything works, okay, assuming that it works, the lectures are all recorded. It's slides and my voice. You don't get to see me again, but you get to see the slides and listen to me. So if you have to miss something, send me an email, let me know you're not here, and you can review it online. Okay, have a good day.